Hello, welcome to Math 332 for the spring semester of 2019, and this is our first video. There are going to be videos like this throughout the semester. I will use these videos to supplement our lecture or to talk about topics which we don't have times to cover in class, such as the videos today, where we're going to do a review on matrices and its basic operations. We're going to follow the text, sections 1.3, and at the end of this video we are going to talk about two very important point of view in terms of matrix multiplications, which you might not be that familiar with. All right, okay, so let's get right to it. First question we have is, what is a matrix? So a matrix is nothing but a rectangular array of numbers, and the numbers in the array are what we call entries. All right, now that's pretty straightforward. So before we move on, we want to talk about very important concepts. We want to be able to talk about the size of a matrix, like how big a matrix is. We should be able to have some kind of way to quantify that. And before we go into that, there's another information you need to have right away, which is when we deal with matrices, the information on the row is always mentioned first, and then only we mention the information on the columns. All right, so for matrices, row information is more important than the column information. We mention the row informations, then we mention the column information. For example, in regards to the size of a matrix, say for example this matrix, if we want to know how big is this matrix, we will first see how many rows we have. So for this matrix, we have 3 rows and then 2 columns. So we say that this matrix is of size, so the size of this matrix is 3 by 2. So the first number here refers to the number of rows of that matrix, and this number here will refers to the numbers of columns for this matrix. So for example, this will be 1 by 4 matrix, okay? 1 row and 4 different columns. And then this will be a 3 by 3 matrix, 3 rows and 3 columns. And this will be a 2 by 1 matrix, and this will be a 1 by 1 matrix. Now there's some special terminology that we're going to use a lot during this course, is that this particular 1 by 4 matrix is also known as a row vectors. This is known as a row vectors. And here, this 2 by 1 matrix is what we're going to call a column vectors. All right. So we'll come back to that later. We're going to mention that a lot in our classes. Okay. So these are how we talk about the size of a matrix. And the size of a matrix is important because we are going to use it to talk about how matrix operations. All right, so before we do that, let us look at the notations for matrices. So the convention is that we always use the capital letters to denote a matrix, and then we use the small letters to denote the entries of a matrix. Say, for example, you have this general matrix A of size 3 by 4, and these are the entries. Now, one way to write these entries is to write like A11, A12, I provide the indices like 11, 12, 13, 14, A34, so on and so forth. Now, the first question I have for you is that what do you think the 11, the A11, what does this first one stand for? Now, as our general guideline, as you remember, that the first information here is about the row. So this is the first row, and the second number here refers to the first column. So for example, A34 is the entries of the matrix on the third row and the fourth column. Okay, so this is on the third row and on the fourth column. All right, so this number here will always refers to the row, position of the row, and here will refers to the position of the column. General principle from the first time, from before, we mentioned that the information on the row is always mentioned first. Right, so for general m by n matrix, you can write the indices, okay, the entries like that. You can label all the entries using these indices. So you can see that here we have m row. So this is m row. This is m by n matrix. You have m rows, and you can tell from here that we have n columns. So this is a m by n matrix. Okay. Now that is the convention. We kind of have to follow the conventions because otherwise it's going to be very confusing. just like in chemistry, right? For water, we write like H2O, and you write like OH2. It's going to confuse a lot of people. So make sure you use the conventions. Use capital A for matrix, and then for the entries, okay, of the matrix, you usually write like this: Aij. Small letter A and I here will refer to the position of the row, and J here will refer to the position of the column. Now, sometimes a matrix can be a square matrix, which means they have the same number of rows and same number of columns. In that case, we can talk about the diagonal of the matrix. So the diagonal of matrix is for a square matrix. It's going to be here. These are the entries A11, A22, A33, all the ways to A and M. For a matrix which is not square, which we call a rectangular matrix, then we cannot really define the diagonal of that matrix. So the diagonal of a matrix is basically a special property for a square matrix. Okay, so this is the conventions and notations on how to write a matrix with its entries. Okay, now, so moving on, we want to be able to talk about, before we even be able to talk about matrix addition, subtraction, all that, we want to talk about under what circumstances we can say two matrices are the same, right? Okay, so the first criteria is obvious. We must have that these two matrices have the same size, right? So for example, if this is a 2 by 3 matrix and this is a 3 by 5 matrix, then we know they are definitely not the same. But they can also have the same size, 2 by 3, 2 by 3. But you know, it doesn't really have to be the same unless all the entries of this matrix A and all the entries of this matrix B are the same. So that's the definitions of equality of matrices. You can read all this thing here. It's pretty straightforward, but it's critical though. All right, so now we want to talk about matrix operations. So just like numbers, we should be able to add the numbers, subtract the numbers, multiply numbers. So we want to be able to do the same for matrices. So we want to add matrices, subtract matrices, multiply matrices, and so on and so forth, right? So before we can talk about the addition of matrices, so all this operation, addition and subtraction and all that, we have to make sure that those matrices are compatible for these operations. So for addition and subtractions, these operations are compatible if and only if they have the same size. So as you can see here, our A is of size 3 by 4. Our B here is of size 3 by 4. So they have the same size, so they are compatible in terms of addition and multiplications. All right, so we define addition and subtraction. I'm sorry. So for addition and subtraction of matrices, we have to first make sure they have the same size. Then we say they're okay, they're compatible, so that they're compatible in the sense that they have the same size, compatible also in terms of addition operations and subtraction operations. For multiplication, where we say compatible, it will mean something else. We'll talk about that in a second. So right now, we have matrix A and matrix B. They have the same size. They are compatible in terms of additions and subtractions. And the way we add them is pretty straightforward. We just add the corresponding component together to get this. If you want to subtract, we subtract the corresponding components and get this. Same thing too. Let's say we have 5. We have 0 here. We add this 5 to get this. We have 0 and then subtract 5 to get this. That's pretty easy. Now, for multiplications, there are two types of multiplications. One of it is called scalar multiplications. So which basically means that take a matrix, it doesn't really matter what size is that matrix, and if you multiply that matrix with a number, then what happens is just look at every entries here, and then you multiply with that numbers. So you have this. All right, so the size of the matrix will not change if you multiply a scalar. If this is a matrix of 2 by 3, so if you multiply a number, let's say -1, it will still be a 2 by 3 matrix. Okay, so scalar multiplications will not change the size of the matrix. All right, so but there's also another type of matrix multiplications, which we call matrix multiplication, which is like we want to take a matrix A and matrix B, and we really want to multiply them together. Now in this situation, first of all, they have to be compatible. So the compatibility here is a little bit subtle compared to what we have for addition and subtraction. So in order for these two matrices to be compatible in terms of multiplications, So let's say here, let's look at this example here, this example here. So your A here is of size 2 by 3, and then B here is of size 3 by 4. And we say that these two matrices are compatible in terms of multiplications if and only if the number in the number here are the same. So if these two numbers are the same, then we say that they are compatible. And the products, after you multiply them out, will be of size 2 by 4. The 2 is coming from here, and then the 4 is coming from here. So I haven't told you how we multiply them together yet. I'm just saying what are the criteria. So the criteria is that the inner number has to be the same, and after that, we also know the size of the resultant matrix, the multiplications, which is of size 2 by 4. So, which means that they have 2 rows and 4 columns. So, right, as indicated here, we have 2 rows and we have 4 different columns here. Now, how do we define matrix multiplications? Well, so we know there are 2 rows and 4 different columns. So let's say we pick these entries. This is on the second row, and the third column. So in order to get that, again, start with the row first. You look at the second row of the first matrix and multiply with the third column of the second matrix and circle them. And then you take 2, multiply with the 4, take 6, multiply with the 3, take 0, multiply with the 5. And then you take the sum and then put it here. That is the entries, the 2, 3 entries. This is a 2, 3 entries, right? So if you call this matrix C, this is a small c, and this is 2, 3. This is a 2, 3 entries. This is a 2, 3 entries of this matrix multiplications, the resultant products, all right? So same thing here. If you want to look at this resultant products, these entries here, this is on the first row and the fourth column. So in order to get these entries, you have to take the first row of the first matrix and the fourth column of the second matrix. And then you take this number, multiply them together, take this number, multiply them together, take this number, multiply them together. And then you take the sum of all these products. And that is how you get these entries. So in order to figure out what are all the entries of A, B, you just do the same for this, and then here you go. That is how we define matrix multiplications of 2 different matrices. Okay, so so right here is basically a summary of what I just told you. So right here, make sure that if you want to multiply 2 matrices, the inner number have to match, and then the outer number give you the size of the resultant product. Okay, now from here, you probably can see that in general, your matrix multiplication AB might not be the same as BA. Let's say we look at this example. This is of size 2 by 3. This is of size 3 by 4. So B is of size 3 by 4, and then A is of size 2 by 3. And you can see that BA are not compatible in terms of matrix multiplications. We cannot multiply BA together. So obviously AB is not the same as BA, right? Which is kind of weird because for numbers, if you take 2 numbers, 2 real numbers, and multiply them together, they are the same. AB and BA are the same, but not for this. So we can also show that even when situations allow them to be compatible, let's say this is a 3 by 3 matrix, this is a 3 by 3, 3 by 3, 3 by 3. So they're all compatible, but there's still no guarantee that this are going to give you the same matrix, right? So the 2 matrices might be different. So that's why we say that matrix multiplications is not commutative. So they are not commutative. So for matrix multiplication, they are not commutative. This sets apart the difference between matrix algebra and algebra involving real numbers. So this is one of the things that you have to pay attention to. Okay. Now you should be able to read all this. This is just a more example. It's a small example, and I want to spend a couple more minutes to talk about one thing, which is why do we define matrix multiplications that's so complicated, in that complicated manners? Well, there are many reasons, but one of the key reasons is that if you define matrix multiplications like that, Then we can code this system of equations, which is the things that we want to study in linear algebra. We can code the system of equations into a matrix form. Now, remember that, so this is a matrix A, this is the matrix A, the coefficient matrix. Your X here is the column vectors, and your B here is the column vectors. Now let's check the size. So this is of size m by 1, m rows, 1 column. This matrix here have m rows and then n columns. And then this column vector here has n rows and 1 column. So they are all compatible. And the way we define matrix multiplication allow us to do this, right? So you can see that in order to get B1, you have to take A11 multiplied with X1, A12 multiplied with X2, all the way to A1n multiplied to Xn, and you set it equal to B1. And this gives you exactly the first equation. So one of the main reasons that we define matrix multiplications in that complicated manner is so that we can code the system of equations and put it into a matrix form. So by doing so, we can study the system of linear equation by simply studying their corresponding matrix systems. All right? Okay, so this is one of the questions that you might have. Why do we define the matrix multiplication that way? Now, so this is the things that you need to know, but you should be able to read it. So just have to make sure you know what transpose of a matrix is, what trace of a matrix is, and also there is a matrix that we call augmented matrix. We're going to use that a lot. You should also know what augmented matrix is. And so that's basically it. But so right here we want to talk about one very important consequences of all these matrix multiplications. Right now, this is important, very important. You should have all this intuitions and all this information. So we're going to use this throughout the course. So the thing is, now you have a matrix A, size 3 by 3, and then you have a column vectors size 3 by 1. They are compatible, obviously. The inner numbers is the same, and we can see that the resultant matrix is of size 3 by 1. So you should have 3 row, these are 3 row, and only 1 column. Now, so if you follow the definitions, you take A11 and multiply with X, A12 multiply with Y, A13 multiply with Z. This is what you get. This is what you get after matrix multiplications, following the definitions. But instead of writing it this way, do you see that they all have the X, they all have the X right here? So basically, we can write this guy like this. So, and also the one says with the Y, you can kind of like factor out the Y, which is just a number, and write the coefficient A12, A22, A23, A32 as this column vectors, and then write the same thing here, factor out the Z, and write this coefficient here as this column vectors, and you can see they are the same thing, right? We can add this we can add all this because this is a 3 by 1 matrix, 3 by 1 matrix, 3 by 1 matrix. They're compatible. And also remember that after you multiply a number, a scalar with a matrix, it doesn't change the size, right? So all this thing is defined, and all this thing is the same as this. So also, again, this is a number, so you can write in the front or at the back. It doesn't really matter. Now, what it says is that if you have the x, y, z multiplied with a matrix, what happens is that the resultant A, matrix A with the x, y, z, what you get is the linear combination. So this is also a big concept. We're going to use that a lot. This is throughout this course, actually. Linear combinations. Okay, so what I'm saying is that the resultant of these matrix multiplications give you a linear combination of the column. So it's like I have the column of this matrix, and then I'm combining it. We multiply a constant, and then we are combining it with the second column, A12, A22, A32, but we kind of like scale it a little bit, do something here, and then plus Z, and then here A13, A23, A33. So you have to change your perspective from the typical matrix multiplication to this. They are the same thing, and I want you to be able to see it both ways. So this is critical. And in class, sometimes you'll see me writing all this thing using all this shorthand. So this one means that it's not just a number, C1. This is the column vectors, column vectors, column vectors. And if you multiply x, y, z, you have x multiplied with these column vectors, y multiplied with these column vectors, and z multiplied with these column vectors. All right, so this is very important, and you must be able to see these two uh, matrix multiplication. The product of this matrix multiplications give you this. You also have to see it this way. Now there is another one. We don't use it quite that often, but we actually do use it. Is the another point of view to what happens if you take a row of a matrix, a row vectors, and then multiply it with this matrix A. So if you follow the definitions, obviously they are compatible. You can multiply them. Let's look at the size. So this is 1 by 3. This is 3 by 3. The inner numbers is the same. So the end result is a 1 by 3 matrix, which is one row and then 3 columns. 1 column, 2 column, 3 column. Okay, so if you follow the definitions, x times this, y times this, z times this, you have this. And then for the second row, second columns, so you have to take first row, second column. So you have to take x of this, y of this, z of this, and you have this. So instead of looking at it this way, you can also kind of like factor out the x. You have x everywhere here. You can factor out the x and write it like this. You can factor out the y and write it like this. You can factor out the z and write it like this. So they are the same thing. So you should also be able to see that when you hit it, you hit a matrix with row vectors right here from the left hand side, you get this. Okay, so this is kind of like a linear combination of the row, right? So this is the first row of this matrix A, second row of this matrix A, third row of this matrix A. So it's kind of like linearly combining the row vectors. Previously you have linear combining the column vectors, but this is a linearly combining the row vectors. These are all the row vectors. These are all the row vectors. These are all the row vectors of A, the matrix A. Matrix A is this one. Right. Now, one way, one good useful application is when we talk about permutation matrix. But you'll know what permutation matrix means in a second. So say, for example, you have this matrix of 0, and then you have 1. So let's say when you really want to multiply them, you would do this. This is the usual point of view. But based on what we learned just now, you can kind of think of it this way. So you have 0, hit it with this first row, which is 0. You take 1, hit it with this row. That's the reason why you get this. And then you take 0, hit it with this row. So the matrix multiplication with this row, with all this matrix, give you this. All right. So you can see that for this guy, so you take the first one, hit it with this row, and then 0, 0 with this row and that row. So you get this. So do you see what happened? Why is it called permutation matrix? Because the product is kind of like basically rearranging the row of this matrix. So originally you have here, you have like, this is the first row. Okay, this is like the second row. This is like the third row. But when you multiply with this matrix, you got it. The second row now is here. You get interchanged with the first row, and then the third row stay the same. You can kind of very easily see that if you have this perspective. If you have this perspective, right? If you can see that, if you can see that this matrix multiplication actually give you this, then this will come in pretty handy. You can kind of see it. So the reason why we call it permutation matrix is they are permuting the row of this matrix A. So you should also, this is also important, you should also be able to use this perspective to see stuff. So these 2 point of view are kind of new. I don't think you kind of seen this before. So make sure you know this. We are going to use this a lot, okay? And that's the end of this video, and there will be a test in this topic. So make sure you study, watch the videos, or like read the books, and I will see you in class. Bye.